Hello and most welcome to 1117. It is progressing hastily here. One cannot really complain about the speed that we're progressing presently. And in this speed, a sort of mistake occurred yesterday. What sort of mistake? Well, it was a mistake of, how can I explain it? I usually take text and I want to present something coming from fractality and chaos theory. We were studying earlier, and that's a while ago, in Egvena, James Gleick, and also somebody who wrote about Blake, William Blake, and chaos theory. The name eludes me at the moment, but I remember it was very interesting.
The Derrida specialist.
You
remember the...
Plotnotsky.
Thank you, Plotnotsky.
Thank you. Arkady Plotnitsky, ending with a Y. I would put it in the description. He is an excellent Derrida interpreter. And I would say he's the first one who made the jump from quantum mechanics to deconstruction, contemporary philosophy. And in the book the first book I read, it included not only Jacques Derrida, but also the French philosopher Georges Bataille. And he used Georges Bataille and his general economy to help me understand from a very abstract plane what quantum physics is. To be honest, it's a very weird way I got into quantum mechanics. I started in the abstract. Usually it's just the opposite. One looks at the experiments and so forth, but it seemed I am one of those people who prefer the abstract to the real, which we will mend now, because I have found by happenstance some book called The Cosmic Hologram, Information at the Center of Creation. And it's written by Jude, and in this case it's a female name, and her second name is, let's see here, Currivan, 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 rather unusual name.
So you think about the spice?
I mean, yeah, it starts with the spice, but not with the Y.
A van is like a car.
Yeah.
Curry van. Van with spices.
Yeah, very good. Van with curry, but forget about the Y. Very good. I don't think that way. Put it on the boot, Kalle. Yeah, good one. And her book is just excellent. It is not my usual audience at all. I would say the book is directed toward New Agers. And I had a brief look yesterday at the comments in Amazon, and there were actually some scientifically inclined people, and there are no commentaries or criticism when it comes to her scientific ideas. Some little details of insignificant character is coming up, but the book is very, very expansive. It covers all of, I would say, the whole field, going from fractality, chaos theory, quantum mechanics, and to the regular, ordinary world. And the greatest discovery for me was, which I would take in the next lecture, because my brain still needs to process that, but it was how the two researchers, one was named Julia, still male for some reason, who led to the discovery of the Julia sets, later further developed and becoming Mandelbrot set, how shows that knowledge is also complementary, and knowledge seems to be something by itself. It's very hard to explain, but once you look into it, it seems to have a character of its own. This is, I would say this is an expansion of something called information theory. Information theory, we have something called information, and information is what makes up the universe together with time and space. But here it's not defined as being information. It is knowledge, whatever we mean with knowledge. So information gives more association with facts, things that could be binary, put into a computer and so forth. Knowledge is greater than that. Why is that? Well, fractality doesn't lend itself into binary. It is not 1 and 0. It is fractality, which means that between 1 and 0 there are myriads. It's actually infinite. Well, I'll start here and see what it will take us. I was just thinking, we have the sun. I must be getting dark. I think I should move actually.
Yes.
I didn't notice that. I do have the sun in my back. Sorry about that. See if I'm still visible here.
Yes, it's fine.
I will start with her chapter on quantum mechanics, so you can see, because we are rather well acquainted with quantum mechanics by now, so it will be a segue into her writing. We're at page 84, and it's called Conditions. I don't even more have the sun in my back. Need to turn the whole thing around here. Let's see here. That's better. That's much better.
You're darker than earlier. Okay, no. Now it's fixed.
No,
Okay, you can continue, please.
We will talk about conditions in this chapter, and it's taken from the book, and we are at page 84, so it's in the beginning. And there she mentions quantum mechanics quite extensively, and she's so accurate. She has a God-given sense of quantum mechanics, although she's not of the profession. Something that I think is quite amazing in itself. Initial circumstances that determine the outcome of something. And very fittingly, we have a visitor. This is the very symbol of initial circumstances, a butterfly. It's always used when we talk about initial circumstances in chaos theory. And the reason, unbeknownst to me, for having a butterfly was that Edward Lorenz, on his computer print, when he made the first discovery that initial conditions regulates everything when it comes to weather, it looked like a butterfly. And he kept that butterfly, and the butterfly is still going on even to this day. So his title of his first presentation of the rather immense discovery was "When a butterfly flaps its wings in the jungle of Brazil, will that cause a tornado in Texas. And this is exactly, it's a very good short way of describing what is initial conditions. Very, very minute or partly minute, smaller than minute changes in attitude, modus you might call it, that makes a whole different result. And of course, you have been following the series, you know now I'm talking about the Alice and Bob experiment, where the modus changes everything, and modus that most probably we're not even aware of. So I soldier on. A quote from Leo Tolstoy, author: "One of the first conditions of happiness is that link between man and nature shall not be broken." And I think that is so true. We have broken that link. We no longer know what puts us together with nature. Our sense of what is causality, for instance, is today Newtonian, and I would say that is rather confusing. Simplicity, invariance, causality are three fundamental conditions of our perfect universe. Each plays a major role in how space and time itself is manifested and how embedded information informs physical reality. The realization of the astonishing level of simplicity that underlies the complexity of the physical world often shows up in attempts to integrate apparently diverse phenomena. Sometimes simplicity is found in unexpected revelations of correspondences and complementarities. Regularly, its presence guides the path of least effort or resistance that shows up universally in physical processes. The universal condition of invariance, meaning unchanging or constant behavior, states, for example, that while space and time, as Einstein observed, are each relative to the position of an observer, their integration as four-dimensional space-time is invariant. Very important. So all measurements of the same event as defined by its coordinates in space-time will give the same answer to every observer, regardless of the observer's location in space and time. Indeed, the mathematics of relativity theory actually requires that throughout space-time all physical laws must be invariant. They must take the same form regardless of whether they are measured in a laboratory on Earth today, on a planet orbiting a star in another galaxy a million years ago, or even at the edge of a black hole a billion years hence. The third primary condition is causality. This innate prerequisite of the physical realm always ensures that any cause precedes its effect. Remember that, because this is going to flow through the whole lecture and the next lecture. Cause and effect. This may just seem like common sense, as the inevitable reflects our because as it inevitably reflects our everyday experiences, yet many physical laws appear not to include time and thus the notion of cause and effect. As we look deeper, though, we'll find that vitally causality is built into the fundamental structure of space-time. These three crucial conditions determine and pervade physical physical reality. Let's now see how they do so and how they are key aspects in enabling our universe to exist as a unified and coherent entity and evolve to embody ever greater levels of complexity. Simple. Let's first appreciate the view of Galileo Galilei, the 16th century astronomer and early champion of the Copernican view of the Sun being at the center of our solar system, that the book of nature is written in the language of mathematics. The basic mathematical functions which underlie and are encoded in the quantized bits of physical reality haven't been invented, constructed, or created by human intelligence. They've been discovered. And as a literally cosmic language, all the physicality of our universe, and so its all-pervasive information, can be conveyed in mathematical terms that describe its relationship, transferences, and flows. While all physical reality can be expressed informationally in the cosmic language of mathematics, not all mathematics describe such manifestations. Time and again scientists have realized that the powerful and elegant equations and relationships that describe physical reality are indeed, to paraphrase Einstein's view, as simple as they can be, but no simpler. Being guided by the condition of simplicity and willing to follow where its descriptive mathematics leads reveals further insight that enrich and integrate our understanding of the nature of our perfect universe. Its direction enables us to distinguish the apparent diversity of phenomena from the deep simplicity that underpins their expression. To get a feel for how important this premise of innate and universal simplicity is, let us briefly consider a few examples. In the late 19th century, Scottish physicist James Clerk Maxwell is famous for many things, and he's one of the founding fathers of modern thermodynamics, and he was also one of those ones that helped bring about the understanding of entropy and the thermal death that led to so many preemptive suicides in the late 19th century. Often called the father of modern physics and an all-around good egg, studied the seemingly diverse natures of electricity, magnetism, and light. He built on research by one of the best experimental physicists of his day, or indeed any era, James Faraday, who in the 1830s had begun the process of simplification by discovering that a moving electric charge causes a magnetic field, and correspondingly that a moving magnetic field generates an electric current, something that we looked at in this last Tuesday, where we talked about how a generator constructs a wave, and we can put it upside down, so to speak, so we can get electricity by using a wave, or we can create waves by using electricity. This led Maxwell to realize that rather than being separate, electricity and magnetism effectively mirror each, rather like two sides of the same coin. By depicting them in the simplest of mathematical terms, he was able to unify them as electromagnetic or EM fields. The mathematics also reveal that EM fields travel in waves through space at the speed of light, which he thus realized is a form of EM radiation whose wavelengths are visible to us. Now, we have the first speak of wavelengths and waves. You see how we slowly are getting into quantum mechanics. His powerful depiction of EM fields was able to predict the existence of radio and other non-visible wavelengths of the EM spectrum. Not only, though, are his equations the basis for our global computing communications and many other technologies, but they also form the inspiration for Einstein's later revolutionary insight into the fundamental nature of space and time. In the early 20th century, by taking literally Maxwell's mathematical description of light, that showed it having a universally fixed speed, c, Einstein realized that both space and time are relative to the perspective of an observer. By integrating them into a four-dimensional space-time, he was able to describe physical reality in an invariant way, and one that always preserves causality. Very important. One could say that Einstein's project was to find a significant model that could preserve the causality that was already present when he started his project or his thinking. Where the mathematics that accurately describes a phenomenon seems, however, to be less simple than it could be, a door is invariably open to a more profound and compelling understanding, revealing why it's as simple as it is, but no simpler. Indeed, throughout the history of science, such recognitions have always shown that the actual level of simplicity is minimized to the degree that's required to still enable the existence and evolution of our perfect universe. By testing the limits of simplicity, that at its most fundamental, everything in our universe is purposeful and nothing is washed. I think we move a bit, the sun is moving, and I should move with it. An illustration of this is English theoretical physicist Paul Dirac's equation, describing the behavior of elementary particles, which in the 1920s led him to predict the existence of antimatter, which was subsequently confirmed 4 years later, already 1924. Antimatter has the same mass and is also made of ordinary matter, but it has opposite electric charge. Dirac's equations show that there should have been the same amount of antimatter and matter created at the beginning of our universe. Yet antimatter is currently barely present. When a matter and antimatter particle come together, they annihilate each other in a burst of light. Measurement of light photons and matter within the CMB has shown that by about a billionth of a second after the first moment of the big breath, for every billion or so matter-antimatter pairs that destroyed each other, only a single matter particle survived, which is in itself amazing. The ongoing exploration to understand why the initial complication of antimatter was needed, why the initial simple symmetry of matter-antimatter was broken, and why only 1 in a billion matter particles was left, is helping us answer a very fundamental question of why there is something other than light in our universe. Why is there something rather than...
Close to the microphone.
Why is there something rather than nothing? And this is oddly the very same question that Martin Heidegger posed almost in the same time in his Sein und Zeit. And that is actually exactly the same question in physics and in philosophy. And trying to say that there are two different questions, that obscures the matter completely. Heidegger mentioned, if you do that division, you will never ever understand what being is. It will forever exclude the understanding of being. Another integration aiming to simplify a phenomenon and so understand it at a deeper level was achieved by Argentinian physicist Juan Maldacena at a 1998 conference of string theorists. He presented a paper inspired by the concept of the holographic principle, which, as we've seen, was pioneered by 't Hooft and Bekenstein, among others. He disclosed that quantum fields can be restated as a version of M-theory. And M-theory, as you might remember, I doubt it since it's like 600 lectures ago, but it tries to reconcile quantum and relativity theory. And what he does, he has a holographic boundary. In revealing their correlations, he enabled the holographic principle as a profound and revolutionary new perspective to gain much greater acceptance among physicists. As an added benefit, he showed too how a very difficult problem viewed from one perspective is much simpler when considered from its correlate. Although his great insight is usually known by the decidedly unsimple title of the ADS/CFT, anti-de Sitter conformal field theory correspondence. And what is this holographic boundary? Well, let me give a point from my own view as a lecturer here today. The boundary we are going to delve into further, it is actually the boundary between aletheia and theia. This is where everything is happening. And I usually depict that by think about the fjords of Norway. In the fjords of Norway, the coastline, what we could call the matter side, the stable atomic side, is defined by a holographic fractality, a border. But at the very same time, and this is important, the water is defined. How is the water? What qualities does the water have? And that is very important. Something that we almost, I would say, always we ignore it. Why is that? Well, we see the other thing as just water and being the empty space, the apeiron, not of any significance. Jude Carivan, thank you for the reminder, now I won't forget her surname. Jude Carivan shows it is not to be forgotten, and this is actually a fantastic clue in understanding the working of quantum mechanics in a much simpler fashion. Norwegian fjord can be depicted, one can understand, and one can also be surprised. Yes, I never cared about the water. I'm been just looking at the coastline. And I took the liberty earlier on to check out on the internet when fractality of the Norwegian coastlines and other coastlines or any other hologram, for instance the Föhn, the Jordbunke, we usually only depict the positive side, as I call it, the matter side, but we ignore what is surrounding. Jude Carivan points to this. She points that the surrounding is of equal importance. And to understand what is a holographic boundary, we need to take the surrounding things into into the calculation, then understanding might come. And this is, I would say, this is a shortcut to get into what complementarity is. Otherwise, I'm not even sure it could be understandable. You just accept it and you say everything is complementary. But by understanding that the borderline is where everything is happening, not in the matter side, to some degree not in the water side either, but in the borderline. And how can you tell at the very borderline which is sea and which is terra firma? You cannot. Actually, as you will learn later, maybe in this lecture or next, it is not really of importance to understand the world. Something that we usually would not regard from an everyday perspective. We'll explore in more detail the key breakthroughs, enormous implications, and rapidly expanding perspectives of the cosmic hologram. But for now, it suffices it to say that Maldasena's presentation was so well received by his colleagues that they immediately began a celebratory dance based on the Macarena. Macarena is a famous dance. It is Magdalena in Spanish, actually, the Magdalena dance. So I think that clarified a bit, but there's still some things remaining. And now we delve into space and time, where the holographic boundary is also very, very present. We can better understand how the two other fundamental conditions, invariance and causality, shape the existence and evolution of our universe on large scales by now exploring further the nature of space and time, although here too simplicity will be our guide. As we do, we'll see why space and time need to be relative to the perspective of an observer, while naturally integrating into invariant space-time, how causality is always preserved owing to the finite and constant speed of light. Albert Einstein was only 16 years old when he first followed a beam of light in an imaginary thought experiment. It took him a further decade, though, until 1905, his so-called year of miracles, to publish a series of breakthrough discoveries inspired what he'd first intuited and which culminated in his special theory of relativity. The special theory is called so because it confines itself to describing the special case of motion of bodies moving at a constant velocity in relation to each other. As we'll see soon, it took even Einstein's genius a further 10 years of intense thought to extend his understanding to the so-called general theory of relativity that describes the motions of accelerating bodies. Oh, and along the way to reveal the revolutionary new theory of gravity. But to get a grip on all this, let's begin by returning to the start of Einstein's journey of discovery to examine what I considered one of, if not the greatest insight yet achieved in the history of science, one that's completely contrary to our everyday experience. To explain how radical his conclusions are, let's remember the basic lesson we learned at school about the relationship between two bodies traveling at the constant velocities. Specifically, the velocity of a body is its speed in a given direction. So to keep things simple, we'll just consider bodies moving in parallel or opposite to each other. The rules of motion then state that to arrive at their combined velocity, their velocity should simply be subtracted from each other if they're moving in the same direction, or added if they're moving in the opposite direction. We can clearly appreciate and experience this. For example, we're in a car, say traveling in the middle of the lane of a 3-lane highway at the constant velocity of 64 kilometers. On the inside lane is a slower truck traveling at, say, 60, and in the outside lane a sports car is traveling at 70, much quicker. To determine our relative velocities is easy. The relative velocity between us and the slower and faster vehicles is 5 kilometers per hour in each case. And the relative velocity between the sports car and the truck is 10 kilometers per hour. Simple math. On the other side of the central barrier, say a vehicle is traveling in the opposite direction to us at the same average velocity of 64 kilometers per hour. While safely separated by the barrier, our relative, this is important, our relative velocity is a whopping 130 kilometers per hour, as in this case our velocities are additive. All this is so in tune with our common sense that as drivers we don't tend to give it much conscious thought as we weave in and out of traffic. But as Einstein discovered, light doesn't operate in this commonsensical way. And realizing this when he scrupulously followed where the logic of Maxwell's electromagnetic equations led, he was forced to acknowledge that neither does space nor time. To take our next step in understanding what he discovered and its implication, we first need to define what we mean in our everyday example by our 65 kilometers per hour velocity as we travel along the highway. The speedometer is an instrument to check speed that tells us that this is how fast we're traveling, measures the car's motion in relation to the road and thus the earth. Terra firma. Our usual and fortunate experience is that when we stand still, the earth isn't moving in relation to ourselves, otherwise we get pretty dizzy. Vitally, it thus forms a stationary reference point not only for our car and every other vehicle on the highway, but also for all objects on closely above its surface. Now, let's turn our attention to Einstein's thought experiment. When he imagined that what it would be like to travel toward, away from, and alongside a light beam. As we've seen some years before him, Maxwell had realized that light is an electromagnetic wave. Critically, his equation that describes EM fields, electromagnetic fields, show that within a given medium, whether space or water for example, the speed of light is constant, always. So although light travels fastest in the vacuum of space and slower in all other media, within each its speed it's invariant. But the equations do not offer any clue as to what the constancy of light speed is measured against. This again is strange when considered in terms of our everyday experiences, where speed is always measured against some frame of reference. And this is highly important. Most people are not aware that the speed of light is constant, even if two beams are approaching each other head-on. The speed would still be the same. And I think this is the very first discovery in the 20th century. This was about 1915. It was the first time the classical idea of the world was shattered decisively, because Newton don't work anymore once a speed is absolute, so to speak. But the equations do not offer any clues as to what the constancy of light is measured against. It's not measured against anything. This again is strange when considered in terms of our everyday experience, where speed is always measured against some frame of reference. There are no exceptions to that rule. Always. In our earlier example, the velocity of the vehicles on the highway is measured against a fixed stationary reference frame of the Earth. But this isn't the case for light that travels throughout our universe, and so, if it behaved in the same way, would need a universal standard frame of reference for its measurement. For many years, an all-pervasive ether had been proposed, not only to try to account for such non-moving reference frame, but also to answer a related mystery. What medium does light travel through in its apparent vacuum of space? Despite numerous efforts to detect it, Einstein's day and ever since, scientists had been continually unsuccessful in doing so. It could be fair to say that ether disappeared. But as I said, by happenstance early on, I would say 99% of the population do still believe in ether, because there is no other way to get the whole worldview together. Let's first take a look at the easier of the two enigmas. What medium does light travel through in space? What is the medium? Remember, all waves in the known universe need to be traveling in some medium, otherwise they won't be waves. Or at least this is the view that still everybody holds, and physicists until the year 1915 or thereabouts. Until Einstein, and with no clue from Maxwell, physicists had viewed the propagation of light as needing some form of medium to travel through. As mechanical waves, sounds need some form of medium, such as air or water, to spread. As the famous tagline from the film Alien noted, "In space, no one can hear you scream." The transmission of visible light and all other wavelengths of electromagnetic fields does not require any such media, because, as Einstein realized, light is an oscillation, very important, an oscillation of the EM field, and the electromagnetic field itself is the medium. What? Universally present throughout space-time. Need to take an extra puff on my cigar. The greater challenge, and correspondingly even more revelatory discovery, arose from Einstein's attempt to answer the other puzzle. Question number 2 here. What is light's universal reference frame? How do we measure it? Remember the cars. They are measured in contrast to terra firma, the ground. Bridge, could be mountain, as we always do in every ordinary example. When we cycle, when we drive a car, when we drive a boat, all examples. So what is the universal reference frame? When Einstein's thought experiment followed a beam of light, he realized astonishingly that the constancy of its speed means that it's constant for any and all frames of reference, no matter how they choose it. Essentially, from wherever and however it's measured, its speed will always be the same. How does that even work? When considered against our everyday experience, this is extraordinary. Think about that you try to check your speed when you're driving according to a car that drives next to you. You will conclude that when using the other car as a reference point, you need to deduct 50, 60, 70 kilometers that car is traveling in. Einstein discovered that to be not the case when it goes to the speed of light. Although the car next to is driving 100 kilometers an hour, 100,000 kilometers an hour, it doesn't matter. The speed of light will still be 300,000 kilometers per second. To see just how unexpected this discovery was, we'll consider another everyday example. Imagine we're traveling in a train on a dark night when another passes by. Unable to see the surrounding landscape for reference as the two trains pass, we'd be unable to determine which one, or if indeed either, was stationary. We wouldn't be able to gauge the absolute speed of either against a stationary reference point. All we will be able to measure would be the relative speed. That is, once you pass a train in the night, you don't know if it's moving or not. You have no chance of finding out whether it's moving or not. It could be stationary. It could be standing at the station you passes, but it can as well be moving from the station at a tremendous speed. If each train had a mirror positioned on its leading edge, we could do this by sending a series of light signals from our train and measure the progressively shortening times it takes them to reach, bounce off the other train's front mirror and return. Say the oncoming train is traveling at 65 kilometers per hour and our train, without our knowing, is stationary. We measure the oncoming train speed at 65. Now, if our train was traveling at 40 kilometers per hour, again without our knowing, we'd calculate the other train is approaching at 105 kilometers per hour. And yet in each case, the oncoming train speed remains the same. However, if instead of being a train, imagine a beam of light is traveling towards us, though of course much faster, regardless of our own speed and unlike an approaching train or indeed any other material object in the universe, we'd always measure the speed of light as a constant amount. Equally, if a beam of light is traveling away from us, our measurements of its speed would be exactly the same, irrespective how fast we ourselves are moving. So even if I was moving close to the speed of light, I don't know if that's possible with my extra weight, the light beam that I send out from my flashlight would still have the same speed. While traveling through a medium such as air, light travels more slowly than in a vacuum. Nonetheless, it will always be measured as propagating at a constant rate. In vacuum of space, we'll always measure the speed of light at its universal speed limit of nearly 300 kilometers per second, denoted by the letter C, as in the famous EMC. From the beginning, it was short for constant, and since that acronym is not very practical, it has been changed to the Latin celeritas, which means swiftness. Rather a fitting word, since there is nothing quicker than celeritas. Einstein's conclusion that through the universe there's no preferred location or direction throughout space, and that all inertial frames of reference, meaning those traveling at a constant velocity relative to each other, are completely equivalent, also reveals that the laws of physics are the same throughout the universe. This is good news. Without the implications of the constancy of light as described by the relativity of space and time, we couldn't develop any cosmological theories that would apply to our universe as a whole. Light and its constancy, as Einstein went on to discover at even more profound levels of reality, enables our universe to exist and evolve as a coherent and unified entity. This universality of physical laws, though has a deeper and unavoidable implication. It took Einstein's genius to appreciate that the constancy of light speed, as measured by all observers, means that the speed they are traveling affects the observations and measurements of space and time themselves. The velocity of an object is measured as the distance it's traveled divided by the time it takes to do so. For example, 65 kilometers per hour. As an object speeds up, Einstein's special relativity theory revealed that time, for example, as measured by a clock, slows down. The clock slows down or dilates. And distance, for example, a measured length along the direction of movement shrinks in perfect correspondence. So what is around us and time gets slower and shorter as we move faster. And this is caused by the constancy, the celeritas of light. You see the turnover here? This is a Copernican revolution that is much greater. It's hard to understand even. These precisely compensating relationships are mathematically described by the elegantly simple Lorentz transformation equation, named after the Dutch physicist Hendrik Lorentz, which also applies to the mass energy of an object. It shows that if a massive object were able to be accelerated to the speed of light, time would stand still, its length would shrink to zero, and its mass would increase to an infinite level. The energy to increase its velocity to light speed would also be impossibly infinite, which is why no object of any mass can ever do so within space-time, and why light itself can only travel at the universal speed limit of c, celeritas, because it has no mass. Space-time. As you see, space-time is now considerably affected. Space-time from 1915 and onwards are no longer constants. The coordinate system of Cartesius is falling. The Newtonian idea of stability in space-time is gone, never to be returned. And that scenario is going to be further and further as we move along the time axis into quantum theory and then into Lorentz's discovery of case theory, and then moving on to Benoit Mandelbrot, and then moving on into Feigenbaum and Minkowski space. So we are on a path now, and if you want to get off the path, you need to do it now, because your reality is starting to dissolve, rumble, and interesting things will happen if you linger on. Stay on this train, so to speak, to use the metaphor further mentioned by Jude Curryvan. Very good, Curryvan, I like that. Owing to the relativity of space and time, different observers will measure the same event from different perspectives. The relativity, however, preserves the constancy of light speed and enables physical laws to be universally applicable. This finite and invariant speed of light is a universal conversion factor that changes units of time into units of space and vice versa. It literally weaves space and time together into a four-dimensional and invariant entity called space-time. A further revelation that our universe is innately interconnected and exists and evolves as a single unified entity. To understand the concept of invariant space-time better, let's first look at how distances in space-time are measured. Although most of us don't usually consider such space-time distances on an everyday basis, we're familiar with one term that does just this, a light year, which is the distance that light in vacuum travels in a year. Combining the speed of light multiplied by times gives us a distance. So as our nearest star, the Sun, is 8 light minutes away, whereas Andromeda, the nearest major galaxy beyond our own Milky Way, as depicted by Stephen Mangold, is more than 2.5 million light years distant. Because nothing can exceed the speed of light within space-time, when we see sunlight, we are actually seeing the Sun as it was 8 minutes ago. And when we use a telescope to view the light from the beautiful Andromeda galaxy, we're seeing it as it was more than 2.5 million years ago. Cause and effect. Owing to the very special flatness of space in our universe, we can use the principles of geometry that we first learned at school, not only to derive distances in space-time, but also discover a mathematical basis for how the nature of invariant space-time ensures that all events within our universe always maintain causality. With the relativity of space and time, different observers can each correctly argue from their own perspective about whether or not two events in different locations take place simultaneously. However, when considered as events in combined space-time, any disagreement is resolved, as every observer will measure the same result. As you see here, the step of 1915 is the first step to unifying the universe, because here even the different perspectives we have that are actually incommensurable, they cannot be dealt with within ordinary physics, because somebody else moving at a different speed, his time will be different, but also his length, and also his actual length of his body, his arms, his bones, his legs, his heart, everything will be different. But this Einsteinian theory sort of makes a wholeness out of that. Instead of having fragmentization, it makes a wholeness. And I would say this is the very first step, first to quantum mechanics, but also to the idea that everything is one. Pandainai. And this is also the striving in Jude Caravan's book, to show how everything is one, because it needs to be understood as well. Unless we understand what has changed, the wholeness will not come. She's very smart in that aspect. It's not enough to jump like 20 steps and say, I want to believe in wholeness. I think that is the problem of the non-dual generation that we see today. They want to believe in spirituality, they wanted to believe in wholeness. They said and say, still to this day, everybody should be friends with everyone and we should treat dolphins as our next of kin. But they are not presenting any new way of thinking. So therefore, I would say, I'm a bit harsh now, therefore their claims, and also maybe the claims of religious sects and so forth, are just hopeful wishes. And I think it's natural to hope for that. And this is also not pointed out by Jude Caravan, but will be pointed out by me. This is the greatest counter-argument to all spirituality, coming from people like Richard Dawkins, but I would say it comes from everyday man. They all discover that people want to believe in those things, but they cannot make it fit together. Who wouldn't want to believe that everything is a wholeness? It's an obvious thing. But we need to understand that everything is in wholeness, and that is a completely different thing. I once met upon a friend. He said he could speak Spanish. He couldn't. And therefore, he hoped that he spoke Spanish, which is a quite different thing. It's a sort of braggart, it's a sort of self-delusion. And by paving this road, as Jude Caravan is doing, going all the way from the first breakthrough, which was quite literally the first step towards quantum mechanics. This is the start, oddly enough, of the revolution of all sciences. She helps us on the path that leads not only to hopeful thinking and wishful thinking and subjective wants and Christmas presents and surprises and fingers crossed things, I will win the lottery and so forth. No, to something completely different, and understanding. And nothing of this world can take understanding away from you, because it's embodied. Your body has always worked in the space-time of Einstein, and as you will see later, your body and your soul has always worked in quantum mechanics, as well as in the fractal set of the Mandelbrot set or the Julia set, and your mind is working in the Minkowski set. Once you understand that, there's no need for any hope. Hope can be abandoned, and you can have true hope that is based on a solid foundation of understanding. Otherwise, I would say we just turn away from reality. We become, maybe, as was mentioned by some Joel, I don't know who it was, intellectual...
Aldorf, what was his name? The Swedish apologist, Joel something.
Intellectually dishonest, something like that.
No, it was a German philosopher with the same name as you, Hans Jonas.
Hans Jonas. Intellectual dishonesty. And I think the atheists and the agnostics and those people who don't care, they easily pick that out. So hopeful thinking is intellectual dishonesty. It doesn't bear the point. They do not embody the understanding. Yes, Kalle?
So if I understand your point today, and Judy Caravan's point is that, okay... Judy Caravan's point in this lecture is that in this fragmented world, the unifying thing would be light, because in contrast to many other things, light is always steady.
Yeah.
So if we study the light, it will also help us to become more unified with everything.
Definitely her point here. And I like this. The thing with Einstein. Einstein, he was forced to do this. He liked it, of course. But remember, Einstein was no religious man. Although he came to understand about unifying principles in the universe.
He was religious in his own way, but his God was different. It was like a Platonic God, not moving, not doing.
Not my cup of tea. I will take a cup of coffee though. Could you hand me the canister? Cheers. Nice strong coffee. And now once more. Oh!
Do
you see the butterfly?
Yes, it's on your shoulder, as in the beginning of the lecture, but you didn't see it.
Was it?
Yes.
Oh, it's gone now, sorry.
But come close to the microphone, please.
What is time? Is the next question. And as you can understand, time and cause and effect are related, or interrelated could be a more precise term. What is time? We previously noted that the entropy of our universe began in its lowest state. In informational terms, the simplest it could be, as entropy has inevitably increased since. This essentially gives the notion of time its so-called arrow or direction. Remember that. This is something we've gone through so many lectures, and it's the arrow of time, usually taken up by Lee Smolin and Julian Barber, but of course it plays a very, very important role in all ordinary thinking. The arrow of time is actually something I will go into one lecture maybe next week. It's what makes people stressed out. For believing in the arrow of time will make you feel that there is no time enough, but that's another subject. I will not digress here, it's too interesting. What is time? Well, we previously noted that the entropy of our universe began in its lowest state. In informational terms, the simplest it could be, and entropy has inevitably increased since. This essentially gives the notion of time its so-called arrow or direction. It's also this direction. We also began to explore how cosmologists are beginning to view space-time as being pixelated at the minute Planck scale, and how space, rather than our apparent experience of 3 dimensions, can instead be informationally depicted as integrated space-time, as a 2-dimensional holographic boundary. And we have the word again. It will return. And where each Planck scale area embodies 1 bit of information. We saw too that the combination of the inevitably increase of informational entropy and such a holographic approach to space-time requires space itself to expand. The corresponding conclusion with regard to time brings us via different route from that of Einstein's journey to special relativity to the innate preservation of causality. In informational terms, a causative event always embodies less information than the effect arising from it, as the effect has to take account of its cause as well as its consequences. In addition, the inevitable flow of entropy means that for each succeeding Planck timescale of 10 up to minus 44 seconds, for each flow of entropy means that for each succeeding Planck timescale of 10 to the base of minus 44 seconds, there will be an incremental change. And this leads us to non-locality, because if space itself is pixelated, how can you have locality? The whole idea of XYZ as delineating where something is takes as its supposition that space is indefinitely dividable. Otherwise, you cannot use XYZ independently from the space it depicts. No matter if you write it on a piece of paper, and oddly enough, no matter if you try to conceive of it in your mind. The Planck length is the smallest length of time. That's how it is. So all of a sudden, the idea propounded by Cartesius and Newton, so highly criticized by Leibniz, has now been proven to be wrong. And that brings wholeness back into the picture. All of a sudden, time can become what it actually is. Not a depiction, but something that is time. Seen from the other perspective of non-locality, despite ever much more sophisticated attempts to do so, most scientists have pretty much given up on trying to exceed the speed of light within space-time, and thus disapprove Einstein's revelation that it represents a universal speed limit for transmitting any information within our universe. However, in the past few years, quantum physicists have used an aspect of the phenomena of non-locality to develop quantum computers potentially capable of processing gigantic amounts of data dramatically faster than our current technology allows. Non-locality, which Einstein famously derided as being spooky action at a distance, was an apparent consequence of quantum theory that he never accepted. In 1964, Northern Irish poor physicist, I add, John Stuart Bell, however, in a rigorous mathematical proof named after him, showed that non-locality is required to reproduce all the physical attributes of quantum theory. Experiments beginning in the 1970s aimed to validate non-locality, and in 1982, nearly 30 years after Einstein's death, Alain Aspect and his colleagues at the Université d'Orsay in Paris proved conclusively its reality. Non-local connectivity is often demonstrated through the creation of pairs of twin particles that share quantum states. Very important, quantum states. Quantum states will appear later on, and it's a bit more than it sounds and a bit different than it sounds, and behave as one single entity. One single entity. They are definitely plural, but they behave as one entity. An effect known as entanglement. If they're then separated and the state of one of the entangled pair is subsequently altered, the other will immediately switch its own state to mirror that of its twin. Regardless of how far apart in space and time they are. It could be billions of light years. And that is proven quite recently as actually that you can have the biggest distance in the known universe. And it was shown from 2 Canarian islands. I only know that one of them was La Gomera. I forgot the name of the other. I think it was Tenerife. I'm not 100% sure. It has been proven, and it's rather remarkable. And this, of course, is pointing to the unity of universe. If 2 things that are separated with the biggest distance in the known universe are still one single entity, then the universe, in some sense, is one thing. Observing and so gaining information about either or both particles of the pair disturbs and upset or destroys their entangled states. In 2014, in a so-called quantum teleportation experiment, a team of physicists at the University of Geneva achieved a remarkable feat that further demonstrated the informational significance of entanglement. They did so by first creating an entangled pair of photons. The first was propelled along an optical fiber cable some 25 kilometers, about 15.5 miles in length, and the second sent to a crystal close to where the pair was created. A third unentangled photon was then targeted to hit the first, obliterating both of them. Here's when the quantum teleportation occurred. The information contained in the third photon, instead of being destroyed, was conveyed in the crystal that also contained the surviving second photon of the previously entangled pair. Félix Bussière, the lead author of the report describing the miraculous experiment, explained the quantum state of the 2 elements of light, these entangled photons, which are like 2 Siamese twins, is a channel that empowers the teleportation from light into matter. The experiment thus proved that the information of the state of the photon takes precedence and is thus more fundamental than its physical expression. Progressively, experiments have proved that the phenomenon of entanglement extends way beyond the quantum scale, beginning with the entangled pairs and even triplets of photons, extended to entangled electrons and large molecules. In 2011, a team from the University of Oxford, led by Ka-Chung Lee and Michael Sprague, even managed to entangle the quantum states of small diamonds, each the size of an earring stud even, and at room temperature, at billions of times larger than the quantum scale, and at a temperature we experience in our everyday lives. Such correlations show that it is reality in the macro world, and at scales at which relativity theory also applies. So they apply at the same time, quantum theory and relativity theory, because a diamond earring will be a size of a microscopic object. I will just turn that off, you don't have to pause. It's just a reminder. What experience has shown is that both quantum and relativity theories are correct in that while such non-local connections are real and transcend the limitations of space and time, no information is actually transferred within space-time, and light's universal speed limit remains inviolate. So still information instantaneously is transferred. This is teleportation, this is telekinesia, this is telepathy. It's impossible because light is still remaining the same speed. As highly technical investigations have shown, though, entanglement is merely a precedent to universal non-locality, which, as Bell's theorem essentially shows, is fundamental for all phenomena predicted by quantum theory, and that have now been overwhelmingly validated by experiments. Integration, combined with the inviolate nature of space-time, universal non-locality offers us profound evidence that our universe is fundamentally interconnected as a unified entity that is underpinned and permeated by information. The universal speed limit exhibited by light ensures that information is transferred at a constant and finite limit within space-time, maintaining causality and enabling our universe to experience and evolve. Yet the innate presence of non-locality enables the holographic boundary that is essentially the informational foundation from which the appearance of the physical world arises to be wholly and simultaneously integrated. And Judy Currivan writes information I, N, and then as a small combination mark. This emerging view also offers an alternative approach to understanding the very special and yet crucial nature of the flatness of space-time and the incredible level of universal homogeneity of our universe. Instead of being problems that have generally been assumed to be resolved by an early inflationary epoch, despite no convincing mechanism for how such a mechanism could occur, how it would end, and its apparently unstoppable consequences in terms of infinite other universes forever branching off it, and critically, no evidence for any such occurrence, the inflationary premise that has become a mainstay of standard cosmology. It is actually a thing of today, and Jude Currivan shows that that doesn't go well with what physics is. And I think they want to put everything together. That's a normal want. They want to unify different theories, but they go about in the wrong way. And so did Everett, and so does still to this day Max Tegmark. And it shames physics, I would say. I completely agree with some critics like, for instance, the late David Bohm, that the many worlds theory is a shame of physics. It's a giving up and letting go into pure faith. The emerging perspective of the cosmic hologram, however, offers another approach to the reality of universal flatness and homogeneity that precludes the requirement for any inflationary process. In considering all that we call the physical reality of our universe as arising from an integrated holographic boundary, flatness is encoded as an informational basis for the appearance of space-time, and universal non-locality ensures the requisite levels of homogeneity from which evolutionary processes can emerge. Such exquisitely tuned information has literally informed our perfect universe from the beginning and will do so until its end. But for now, we've seen that inviolate space-time integrated with universal non-locality engenders that innate simplicity, invariance and causality that are fundamental conditions for our perfect universe to experience even greater levels of complexity and also the emergence of self-awareness. Ingredients. Things that are combined to make something greater. And here is a cite from Urbain Dubois, famous chef and writer. The ambition of every good cook must be to make something very good with the fewest possible ingredients. How? Very well. There is only a single ingredient that makes up our perfect universe: information, expressed as energy and acting through non-entropic and entropic processes. As we've seen, informational entropy increases through the lifetime of our universe. Information expressed as energy, though, is not only universally conserved while continually changing its form, but the flatness of space entails that within the entirety of space-time, the combined total of positive or repulsive energies and negative or attractive energies is always precisely zero. Zero. We'll now explore the truly wonderful interactions through which the various energies of our universe combined in myriad ways to inform and evolve the manifest world. Along the way, we'll discover more about the equivalence of energy and matter, the notion of mass and gravity, and how they interact with space-time, and more about mysterious dark matter and dark energy. Significantly, we'll discuss how various emerging theories attempting to reconcile quantum and relativity theories all seem to require the reduction in the number of spatial dimensions, from the three we are familiar with to a single dimension that combines with time to form a fundamentally two-dimensional space-time, another indication of the holographic foundations of physical reality. And here the most important question here at this stage, at the foundation, and that is, what is energy? While there are many forms of energy can take in our perfect universe, all types are convertible into all others. All obey universal conservation throughout space-time. All ultimately balance each other out to zero. And all energy flows adhere to universal paths of least efforts. For example, the EM radiant, that's the electromagnetic radiant energy of the sun, mainly in the frequency range of the visible spectrum, is converted on Earth by plants and stored as chemical energy in compounds such as sugars and starches. When we eat plant tissue, our digestive process breaks down the plant compounds, converts the released chemical energy into other forms such as electrical energy that powers our nervous system and mechanical energy that enables us to move around. Sometimes heat and work, such as swinging a bat or hitting a ball, are mistakenly considered to be energies. Instead, these are actually processes by which the energies of a system are transferred or changed in some way and where the flow of time matters, and so actually represent flows of entropy. Although this distinction might seem a bit arcane, it's actually very important for our understanding of not only what energy is, but also how it complements the concept of entropy. The attributes of both, as we have seen, can be understood and restated in terms of the first and second law of information, that are the fundamental instructions informing the physical world. Where information is expressed by the myriad forms that energy can take, it is universally conserved, whereas information expressed through entropic processes is always increasing throughout the lifetime of our universe. The most famous equation in the world is reckoned to be the one discovered by Einstein, in which he revealed the equivalence of energy and matter. E equals mc in square, where E is energy associated with a mass m, and c squared is the speed of light squared. Given the size of c square is enormous, the equation shows the incredible amount of energy stored in matter. For example, the energy embodied in half a kilogram of matter, if totally released, could provide all the power needs of a mid-sized city, such as Nottingham in the UK, for a year. While Einstein arrived at that correspondence from his realization of relativity of space and time, their integration into an inviolate space-time, they're also an inevitable consequence of the universal conservation of energy and momentum, and the flatness of space. As we've seen, the early quantum physicists understood that as a consequence of their intrinsic waveform, nature and equivalence, all energy and so all matter have vibrational frequencies. The higher the frequency, the greater the energy. So X-rays with smaller wavelengths and higher frequencies are more energetic than the radio waves with longer wavelengths and lower frequencies. And matter too, given its equivalence with energy, can also be described in terms of its frequency. The equation that defines this is E equals hv. E represents an energy of something and is equal to h, the so-called Planck constant, and universal factor that represents the quantum of action, how packets of energy act through the time of the quantum scale, multiplied by v, its frequency. And this we actually went through Tuesday in the hands of Stefan Mangold, if I remember correctly. So the energy of anything, whether denoted as a form of energy or its derivative matter, can be noted by this universal equation, which is literally as simple as it possibly could be. Finally, as matter can always be restated and described in energetic terms, as energy can be restated more fundamentally in terms of information, so too matter is inevitably informational in nature. So remember that. Why matter matters. And I think that precludes the title of the book by Ian McGilchrist that came actually 3 years later, The Matter with Things. And actually, in some ways, they're pointing to the same thing, which is in itself amazing. Without mass, everything within space-time would travel at cosmic speed limits of c, as do, of course, the massless photons of light. The Lorentz transformation equation describes the slowing down of time as light speed is approached, so that at this universal speed limit, time literally stands still. The same Lorentz equation also reveals that if accelerated, the mass of an object increases to infinity at the speed of light, an impossibility that ensures massive bodies are unable to achieve light speed within space-time. The Large Hadron Collider, or LHC, at CERN, the European Centre for Nuclear Research, which restarted in spring 2015 after a 2-year shutdown and upgrade, routinely has to deal with such relativistic effects. Its immense power accelerates elementary particles to only a few meters per second slower than the light speed, both enormously increasing their masses, and for normally short-lived particles extending their lifetimes by many thousands of times. Very importantly, obtaining mass slows things down, and together with the equivalence between mass and energy, essentially enables the entropic flow of information, so the experience of time itself within our universe. For many years, though, the way in which elementary particles gain mass was a mystery, as there is no indication in quantum theory as to why or how they should do so. However, in 1964, British physicist Peter Higgs was one of 6 theorists who attempted to answer the fundamental question, proposing the existence of a universal field of constant energy pervading all of space, whose interaction with certain elementary particles imbues them with mass. The field and its mechanism to instill mass is now named after Higgs, the Higgs field. At the extremely high temperature of our universe, less than a trillionth of a second after the beginning of space-time, all elementary particles are deemed to have been massless. As the temperature dropped, though, at a certain point, the falling energy of the Higgs field underwent a so-called phase transition, such as what happens when water freezes into ice. In doing so, the field fell to its lowest energy level, essentially freezing that level, and the triggering of its associated mechanism for inducing matter with mass into the fabric of space-time from then onward. In 1993, the UK Science Minister offered a prize, a bottle of good champagne, for the best non-scientific explanation of the Higgs mechanism, which was won by David Miller of University College London. Since translated into other scenarios involving politicians or Hollywood actors, the original envisages a room full of scientists having a party. When a well-known, this is the example, when a well-known scientist enters the room, she causes a bit of kerfuffle, attracting admirers and finding her progress slow down as a result. She acquires mass due to the Higgs field of enthusiasts clustering around her. When a lesser-known person enters, like me, however, fewer people are attracted to him, and so his interaction with the field is smaller and acquires less mass. That would be a fantastic way of losing weight. The Higgs fields and mechanism is an essential component of our universe. Not only does it provide the mass needed for time to unfold, but without it, atoms would be immediately disintegrate. Yet the field's electric charge neutrality also means that it doesn't directly interact with the universal electromagnetic field that pervades all space. So photons remain massless, which, as we've seen, is important to enabling their attributes of light to literally weave space-time together. While both the theoretical field and the mechanism by which mass is derived came to be named after Higgs, for many years they remained merely a theoretical possibility, as the Higgs field is very difficult to detect. The only means of doing so, at least for foreseeable technology, is through the creation of excitation within the field, which are predicted to present themselves as elementary particles called the Higgs boson, and which then act as a mediator imbuing other elementary particles with mass. The Higgs boson is now very, very famous. Many books have been written about it, and many TV programs, and I think there is even a movie about it. It shows that there is an interest in these things that are immensely, but Judy Caravan tries to go to the bottom so we from a layman perspective can really understand, and therefore get the implication, we can get the benefits. The search for the Higgs boson, however, requires very high energies, equivalent to reenacting those at the earliest epoch of our universe, to excite the Higgs field, enable the incredible unstable and short-lived particle to appear. Even then, it's only possible to detect it indirectly by the flow of lower mass energy particles it is predicted to decay into. The only place on Earth where the required high energy conditions can currently be obtained is at the LHC at CERN. It was here in 2012 that the Higgs boson was first discovered by slamming together high energy beams of protons and observing the decay particle outcomes. With a mass of around 130 times that of a proton, the Higgs boson was found to be in line with theoretical predictions, and its discovery led in 2013, nearly 15 years after the breakthrough insights, to Higgs and his colleague Francois England becoming or being awarded by the Nobel Prize in Physics. Well, I just conclude here. My back is hurting me. Slowly we go into the process of establishing a foundation for understanding the unity of the universe. And Judy Caravan wants us to really understand. And although some of these things sounds complicated, the very zest of it is not. And by repetition and explication, it could be understood why the universe actually, literally, factually is one. And also later on will come an explanation that from a simple thing that one could be drawn on a piece of paper, one can understand the unity of the world. But actually in this case, it's better to go the historical way, see the evolution of what came to be the unity of all things, from circa 1900 or 1900 exactly, which is a good date to sort of pinpoint, going forward in history, seeing the development, and then entering into the Mandelbrot set later on. And then you will be relieved everything gets so much easier. But it wouldn't get easier if the foundation weren't laid. Then I think the Mandelbrot set would be understood only as geometrical mathematical thing. It is a lot more than that. It could be one of the most amazing things that I ever seen on a piece of paper anyway. And oddly enough, it is not exclusively on a piece of paper. It's everywhere, even in our minds. I say thank you very much and have a very pleasant afternoon. I will now cure my back. Bye bye for now.